You know that little padlock icon you see in your browser's address bar 100 times a day? It's supposed to mean your connection is secure. But what does that really mean? What's actually happening in those few milliseconds before a website even loads to make sure no one's listening in?
Well, it's not just a simple lock. It's a high-speed negotiation, this really elegant secret handshake called Transport Layer Security, or TLS for short. Think of it like a carefully choreographed dance that lets your computer and a website agree on a private language, even though they're talking to each other across the wide-open public internet.
So, why is this secret handshake so absolutely vital? Well, it's because the internet, at its core, is just an open network. Without something like TLS, sending a password or your credit card number online would be like shouting it across a crowded room. Anyone could potentially hear it.
Now, you've probably heard of HTTPS. This process, TLS, is the S part. It's what puts the secure in HTTPS. But honestly, its job is so much bigger than just making sure your online shopping is safe. TLS is like this invisible shield protecting huge chunks of our digital lives. It's what secures your emails as they bounce between servers. It's the tech that creates the secure tunnel for your VPN, keeping your traffic private. And it's how thousands of apps and services, the ones running in the background, all talk to each other securely. It is, quite literally, the bedrock of digital trust. Okay, so before this handshake can even start, both sides, your device and the server you're talking to, they need to agree on what tools they're going to use. And for this, they've got two very different kinds of secret codes in their toolkit.
On one hand, you've got what's called asymmetric cryptography. It's a little bit slower, but it has this kind of magical property. Think of it like a public mailbox. Anyone can drop a message in, but only you, the person with a private key, can open it and read what's inside. Then you have symmetric cryptography. This one is blazing fast, but it has one catch. Both sides need to have the exact same secret key to begin with. So the entire goal of the handshake is to use that slow, clever mailbox method to securely agree on a shared key for the much faster symmetric method that they'll use for the actual conversation.
And that brings us to the two main acts in the TLS show. First up, you have the handshake protocol. This is where all the negotiation, the identity checks, and that all-important key exchange happens. Once that's all settled, the record protocol takes over, using the brand new keys to protect all the actual data for the rest of your visit.
All right, let's go behind the scenes. It's time to listen in on the actual back and forth conversation. This is the handshake itself, step by step.
So, your browser, the client, kicks things off. It sends a message called the client hello. It's basically saying, hey there, I'm a modern browser. I support TLS version 1.3. Here's a whole menu of the different encryption methods I know how to use. And just for kicks, here's a big random number just for this chat. The server gets that menu, and right away it sends back a server hello. It looks at all the options the browser sent and says, great to meet you. From your list, we're going to use the absolute strongest protocol and encryption we both support. Oh, and here's my random number. Just like that, they've agreed on the rules of engagement. Next up, and this is crucial, the server has to prove it is who it says it is, so it sends over its digital certificate. Your browser then becomes a detective. It checks three really important things. One, is this certificate signed by a trusted authority? Two, does the name on the certificate, like google.com, actually match the site I'm trying to connect to? And three, is it still valid or has it expired? If it passes all three checks, your browser gives it a thumbs up. Okay, so now they trust each other. But here is the million-dollar question. How on earth do they agree on a secret key for that super fast encryption when their whole conversation so far has been happening out in the open? This is, without a doubt, the most clever part of the whole process. In the old days, they used a method that turned out to have some weaknesses. But today, the modern web uses a far better method called ephemeral Diffie-Hellman. The magic here is almost like mixing paint. Imagine both the client and the server secretly pick a private color. They then each mix their private color with a common, public color, and they send the mixed results to each other. Now here's the trick. Through some clever math, each side can take their own original private color and the mixed color they just received, and they can both independently create the exact same shared secret color. They end up with an identical secret without ever having to send their original secret ingredients over the wire. This incredible method gives us something called perfect forward secrecy. What that means is because the keys for this specific session are temporary, they're just for this one conversation and get thrown away when you close the tab. Even if a hacker months from now managed to steal the website's main long-term key, they couldn't go back in time and decrypt your past conversations. Each session is its own sealed vault.
So with their identities proven and the secret ingredients exchanged, all the pieces are finally in place to open up that secured tunnel.
And here's the final kind of mind-blowing piece of this puzzle. The actual encryption keys are never sent across the internet. Nope. Instead, both the client and the server use that shared secret they just created, along with those random numbers from their hello messages, as ingredients for the exact same recipe. And poof, out pops an identical set of session keys on both ends, created right there on the spot.
To make sure everything worked perfectly, they each send one last message. It's called a finished message, and it's the very first thing they encrypt using their new session key. If both sides can decrypt the other's message, that's the final confirmation. The handshake is a success. The secure tunnel is officially open for business.
And now we get the payoff. The record protocol takes over. All your actual data, the request for the web page, your login info, everything, it gets chopped into little records, encrypted with that session key, and sent through the secured tunnel. It's now protected by confidentiality, so no one can read it, and integrity, so no one can mess with it.
But you know, this technology isn't just set in stone. The digital handshake is part of a constant arms race, always evolving to get faster, stronger, and more private.
And this evolution has made the entire web feel so much faster. Just look at the difference between the older TLS version 1.2 and the modern standard 1.3. The old way required 2 full back-and-forth round trips between you and the server just to complete the handshake. TLS 1.3 completely redesigned the process to get it all done in just a single round trip, shaving precious milliseconds off connection times.
And it really wasn't just about speed. More importantly, TLS 1.3 made the web fundamentally more secure by default. It just ripped out all the old insecure options. It made perfect forward secrecy mandatory, not optional. It even encrypts more of the handshake itself to hide information from anyone snooping on the network. It basically forced everyone to take the most secure path.
So the next time you see that little padlock, just remember the incredible, high-speed cryptographic dance that just happened in the blink of an eye. TLS is a living protocol. It's a testament to a massive global effort to build a more trustworthy internet. It's this constant balancing act between security, performance, and privacy. And it really leaves you with one final thought. As our computers get ever more powerful and new threats emerge, what is the next generation of the digital handshake going to look like?